Hi, I'm Dr. Montgomery, and in this video we'll be working through an example with an RL circuit, resistors and inductors, here with a couple of sources, independent sources, as well as a dependent source here in this case. What the problem is basically asking us is what is the voltage across this 2 ohm resistor going to be as a function of time after t equals 0. And at t equals 0 specifically, we're going to have this event in the circuit where I'm going to take this switch, which is currently closing this loop. I'm going to flip it so that I'm now connecting this middle branch right here. And we want to basically try to evaluate how is this voltage going to change after I do that. Okay. So first of all, I'll take a minute to maybe copy this down in your notes, and then we'll get started into looking at the initial conditions and sort of evaluating things from there. Okay, so now thinking about to find V of t, as we know with RL and RC circuits, and really any RLC circuits as well, we need to sort of establish what the initial conditions are, okay? In this case, we see that before I flip the switch, I have the switch in the closed position here, whereby I'm connecting my inductor and this resistor, this dependent source, that's connected up with this 3 ohm resistor and the 24 volt source here. So notice that because this branch with the 8 ohm resistor and the 20 volt source, it's not connected to the circuit on both sides. Therefore, there can't be any current flow through this branch. And so, for sake of establishing our initial conditions, these two elements will not come into play at all because they have no effect or no impact on any voltage or current in the rest of the circuit. Okay. So if we look then at maybe establishing kind of a loop equation, let's say around this side of the loop. Let me indicate it, yes, in this direction here. Okay, so I'm going to write an equation that describes the voltages around this loop here. And note that in this loop specifically, I have this current I naught that's been defined for us. And we know that this current I naught relates back to what the voltage is across this dependent source, because that's given by 4 I naught here. So as I write this loop equation, I can just use that current I naught just in the same way we think about writing mesh equations, but here the mesh current, if I wanted to say the mesh current specifically, we already know is defined as this current I naught. So that's what I will use for that specifically. So in writing that, again, this would be a KVL type of expression. The voltage drop across my 3 ohm resistor, of course, again, voltage equals current times resistance. So this would just be 3 times I naught. The voltage drop there. We have a voltage drop across the 24 volt source, so I add that into the equation. Come around again, these two elements, the 20 volt source and the 8 ohm resistor, have no impact, so I'm just crossing over that branch because it's not connected. And then I see I have a voltage rise here, so it would be subtracted off of the quantity 4 I naught. And that's the last element that I have just in this single loop right here. And so I just have those 3 quantities as we have there, right? So now just solving for this, we only have one unknown, so here we can establish right off the bat that our current I naught is going to be equal to 24 amps, okay? So then in thinking about, because we know that we have that current I naught flowing in this direction, what we want to do is then define what would be the voltage ultimately, again, at the initial condition when we're already at steady state before I've flipped the switch here. What's this voltage on this side here? Well, to do that, if we thought again about a loop equation, so let's maybe think about a loop going in this direction. Okay. Well, we have 3 elements here. We have the inductor, we have the resistor, and we have this dependent source. Now again, remember, if we're at steady state, the inductor is already fully charged up, and we know that a fully charged inductor just acts more or less like a short circuit, meaning there's no voltage drop across that element. So if we were to write a loop equation around this side of the circuit, we would just have the voltage V as our voltage drop coming around the loop. Then I have a voltage rise again across 4 I naught. So that'd be V minus 4 I naught equals 0, thereby telling me that my voltage here would be equal to 96 volts. Again, just taking this quantity we already found for I naught, plugging that into this expression, solving for V, gives me that initial condition for my voltage right there, okay? Let's see, further on from there, if I wanted to just for sake of establishing what the initial current through this inductor is, so let me call that I sub L, okay, the current through the inductor, I could find this. Again, we're talking about the initial conditions before the switches change positions. In order to find this, I know that if I've established what this voltage is across my resistor, again, just using Ohm's law then to figure out the current. So this would be the voltage, sorry, I kind of messed that up there. It should be 96 volts over the resistance here, 2 ohms, giving me 48 amps of current. Here again, now I have 48 amps of current flowing in this loop. I naught, we already found, was 24 volts. That is the current flowing on that loop here. And this pretty well then establishes what all of our initial conditions are. So let's say that we know V at 0 minus here, which is going to be the same as what it is at 0 plus, meaning after I close the switch, that is going to be this 96 volts. Okay, so our initial voltage there. And again, the reason I know this, because of the fact that I know that my current, my inductor current at time 0 minus, has to be the same as the inductor current at time 0 plus, which is this 48 amps that we have right here. And so because I know that this current cannot change, that's the same current that's traveling through that resistor right there. So that's how I know this expression to be valid, because if the current's not going to change to that resistor, then of course the voltage would not be able to change. Again, just talking about instantaneously before and after I flip the switch to the other position. Okay. All right, so that establishes kind of our initial condition that we need. Now let's think about how do we define the time constant that we will use in our expression relating what the voltage as a function of time is. Let me take a minute to erase this, and then we'll examine the problem to figure out that part of it. Okay, so now moving on to thinking about how we would get to the time constant tau, right? So this would be, of course, defined as the inductance over our Thevenin equivalent resistance. Again, this Thevenin resistance is with respect to the terminals of the inductor here specifically. But let's think about this. As I flip the switch, okay, I'm moving from this position now to this position. What we see here is that, of course, disconnects my 3 ohm resistor and my 24 volt source. So now I'm connected up to this 8 ohm resistor and this 20 volt source. Well, what happens in particular? We note that this dependent voltage source is depending on the current I naught. And so think about what happens to that current I naught after I flip the switch. Well, of course, that would just have to go to 0, right? Because if this part of the circuit is then basically now disconnected from the rest of the part, I could have no current flow in this branch here. And if therefore, if I have no current flow here, I know that this voltage just has to go to 0, which, as we know, a 0 volt difference across any given element is just basically the same thing as having a short circuit there. So with that in mind, let me take a quick minute maybe to redraw a circuit here to best describe what we're sort of looking at, with the fact that I can basically ignore what's going on here because that's been disconnected, and I have a short circuit here. And then let's think about how we come up with this Thevenin equivalent resistance. Okay, so now having redrawn the circuit just simply by, in essence, shorting out that dependent voltage source, which again, the reason we could do that is because we know that we have no current. This current I naught has to go to 0 after I flip the switch. So therefore, the voltage drop there across that dependent source has to go to 0, therefore giving me the short circuit. So now let's look at what we have. We see that we initially might have thought that, oh, well, I'm connecting up this 20 volt source to my inductor, so it seems like that would start to have an impact on what's going on there. But in fact, because this short circuit sort of occurs due to the fact that we're disconnecting this branch over here, that actually shows us that even though I have connected up this 20 volt source, all of the current from that source is simply going to travel in its own loop, let's say around this direction or however it might be. Whereas the current from the inductor, again, we've charged up that inductor to some initial current. All of that current is simply going to dissipate through the resistor, and because of the short circuit, again, just loop around on itself. So what does then that tell us about, let's say, like the final value of our current as time goes to infinity? Well, again, we would know that all the current has to just discharge through the resistor that we have here, so this would just have to go to 0. So that's be like our final condition for our current. And of course, then if we know that our current's going to 0, then what does that tell us about our voltage V as we go to t equals infinity, well, again, that would, of course, also have to go to 0 volts. If I have no current, I cannot have any voltage there as well. Okay, so now basically what we need to ask ourselves, again, getting back to the time constant with the Thevenin equivalent resistance, is if I'm looking with respect to the terminals of my inductor and asking what is the Thevenin resistance from where I'm sitting right up there, well, here again, because I have this short circuit, that's basically negating this 8 ohm resistor that I have right here. So the only resistor that is impacting this time constant in this Thevenin resistance is this 2 ohm resistor right here. So that's actually a bit easy for us to just say that RTH is simply equal to this 2 ohm resistor right here. Okay. So now then plugging back in to find the time constant, I have a half a Henry on my inductor over my 2 ohm resistor, ultimately giving me a time constant of 1/4 of a second. Okay. And let's see, for sakes of plugging into our equation, if we do 1 over tau, of course this would just be 4 inverse seconds. And from here we can now be able to write our final expression that describes the voltage as a function of time. Okay. So remember, for us to do this, it's basically the final condition, so as V as time goes to infinity, plus the initial condition, minus the final condition, that quantity multiplied by the exponential to the minus t over tau. Okay, so again, remember this is just the general form. We can apply it to any RL and RC circuit where if we know what the final conditions are, we know what the initial conditions are, and we know what tau is, we can basically just plug it into this expression here. So in this case, for this particular problem, again, we've established that as time goes to infinity, the final value is 0 volts, so that'll just be 0 here as well. Our initial voltage, as we established earlier, was 96 volts. And then we have the exponential minus 4t. Again, 4 is just the inverse of tau, so as I plug that into that expression there, that's what that ultimately works out to right there, okay? And this is, of course, in volts, defined for t greater than or equal to 0 seconds, all right? So this was the expression we were ultimately getting to. Now we could also write maybe a similar expression to describe how the current I sub L is changing as a function of time. The time constant tau, of course, would be the same. The only thing that would be different about the equation for the current, let's say IL of t, would simply be that here, in this case, we had the initial condition, which I believe I erased it here, but the initial condition for our current IL at t equals 0. This was a quantity of 48 amps. So if I wanted to write the equation here for IL as a function of time, this would simply be 48 exponential minus 4t. Okay, again, time constant would be the same. The only thing that's different is the initial quantity. And of course, this is in amps here, right? Okay, so that kind of goes through. I hope that makes sense. And again, the main idea here is to be able to initially look at the circuit based on the initial, to establish what those initial conditions are. Again, you only want to be concerned with elements that are connected to the circuit at that time. Second step is to ask yourself, what does the circuit look like after I've thrown a switch or whatever event was occurring? Look at what you might have there. In this case, it was very important to kind of note that after I flipped this switch, that this dependent voltage source more or less went away. We didn't have to worry about it because it was strictly influenced by the current in this branch, which had to go to 0 after I flipped the switch. So then you're asking yourselves, what are basically the final conditions going to be in that circuit, and then figuring out what would your time constant be, tau, and then again plugging this into the general form that we can describe any relationship of any voltage or current in an RL and RC circuit. All right, that wraps up for this one. Hope to see you on the next video.